Hello, everybody. How are you? Anybody still awake? View full screen to the right screen. I'm going to remind you that if you keep your cameras on and your microphones on, then the bonus points. Excuse me. Recording? Yes, recording. I'm gonna go over some PowerPoints today. Talk about finish IR and then talk about mass spec. We'll go over some basic stuff and then go from there. I'm going to go through the PowerPoints first, and then if necessary, then we'll go back to the board. Any news from anyone? How was the weekend? I'll make sure that my phone is off. It's not. It is off. Hi, Devon. Hi, Andres. Hi, Adil. Hi, Cameroon. Hi, Isaac, Jasmine, Helena, Sebastian, Daynard, Margarita, Carla, Ray, Arshnur, Amelia, Roxana, Varun, Evelyn, connecting to audio. How are you guys doing? Okay?
Doing all right.
Doing all right. At the same time. No news? What did you guys do in the weekend? Anybody had any fun other than risking anything health-wise? Oh, I hate my hair. I need a clamp. I don't have any clamp or something, but these are really bad. It just sticks to your hair. I learned it. I don't have it. Maybe I can use my. This can work with the rubber band. Anyway, what's going on? What's going on? That's a nice baby Yoda. Is that baby Yoda or full Yoda? Eshan? Hi, Saeed. Hi, Alana. Hi, Evelyn. Hi, Yasmin. How are you guys doing? Come on, somebody say something. Something random. What did you have? Did anyone have a really good lunch? Don't make me feel bad, okay? Who had the fantastic lunch? Or you can talk about your horrible lunch.
I mean, the Super Bowl's on Sunday. Did anybody watch that?
Who watched that? I didn't. I was driving. I was not driving. I was submitting a grant. That's why I have no memories of that day. Does anyone have any question answer for Isaac? No? I'll sit down in our backyard tomorrow and chop off my hair. I'll have the squirrels eat it. Come on, who had the best lunch today?
I mean, I had leftover pork chops that were good from last night's dinner.
Sounds good. That sounds good, Devon. I actually didn't have such a bad lunch. I had half of a sandwich from Deli Delicious. The sandwiches are pretty good, so I can't complain today. Sometimes I have the stuff from Costco. Okay, you guys ready? I think we are recording except for my one thing. Everything gets recorded. Who's writing on the chat? I normally don't see. No one likes football anymore. Don't say that. There will be people who can attack you. When I was brand new in this country, I was a fresh import from India. I was a really nice, innocent, naive, humble, wonderful young man. I've become a monster in the last 30 years. Um, so I made fun of American football, and you should have seen my research advisor's facial expression. He didn't know what to say. I said, Why do you call it football? You don't even play with foot. You play throw it with a hand. That's a handball. That's a throw ball. That's the stupidest game I have ever seen. This is what I said in I think 1990 sometime, like a year after I got to know him a little bit more. He said, Shantanu, are you going to watch the football? I said, what football? Soccer? He said, no. I've never been a big sports fan. I watch motorcycle racing and that's it. That's the only sports I watch. But then, so he was, I think I offended him. And I didn't even know I was such an idiot. I'm still an idiot. But I was such an idiot at the time. I didn't even know that I offended him. And later on, he said, you should be careful when you talk to someone and make fun of American games. I said, why can't I make fun of anything? I mean, this is a free country. I can make fun of anything in India because people get offended, but I can make fun of anyone in this country. That's what is great about America. Okay, before I say anything more inappropriate and risk my job, let's share screen. Let's change topic. Anybody has any last comment or question?
I have a comment.
Make that comment.
It was my birthday yesterday.
Congratulations, you survived one more.
Thank you. Thank you.
When I was a graduate student, I had a Korean classmate, and he never wanted to learn English. He said, I'm going back to Korea, so why do I bother? Why do I care? So for every birthday, when he's supposed to say happy birthday, he would say congratulations. So since then, we would just joke with each other. Whenever someone would have a birthday, they would say, Carla, congratulations. You met one more, we met for one more year. All right, jokes apart. You guys remember what IR is? It's grammatically wrong, right? It should be we are or I am. That's my old dumb joke. Okay. I don't think anybody, none of my friends laugh anymore. Okay, I'm going to share screen. So Carla, what did you do on your birthday?
I just celebrated here with my family and we ate cheesecake.
Where is our cheesecake? It's only like, how many of us are there? Very few. You could have brought some cheesecake.
I ate that for lunch, actually.
I want cheesecake right now. Okay, back to the annoying world of organic chemistry. Infrared spectroscopy, mass spectroscopy. I'm going to start talking about mass spectroscopy too. Just quick overview. Spectroscopy is an analytical technique to see structure. We cannot see anything, otherwise destroys the alert, no sample. By the way, there is a quiz on Tuesday. So whatever we have covered, the questions will be from there. So I'm going to do a little bit of review of IR before we get into mass spec. So again, you won't see much use of PowerPoint until, unless when we are done with this spectroscopies. Amount of light absorbed by the sample is measured as wavelength, and that varies, and then we figure things out from that absorption. You already saw what happens with IR. IR uses infrared spectroscopy and look at the molecular dance, absorption of the springs and the stretching and vibration of those springs in the molecule. Mass spectroscopy, we'll talk about it. It essentially determines the mass of the compound or fragments of the molecule. Like my hand falls off and it says, okay, Shantanu minus hand weighs, I don't know, 150 pounds, 160 pounds. Shantanu minus two hands weigh, so much, something like that. And sometimes in some mass spec, the molecule breaks down into fragments. That's what they're talking about. Nuclear magnetic resonance, this is really, really cool. And NMR, it basically looks at nuclei, more than one nucleus, and looking at how the nucleus behaves in a magnetic field, you can tell the environment, electronic environment. That's the easiest way I can explain it. Ultraviolet spectroscopy uses like electronic transitions. Electrons jump within a molecule and they absorb energy, and that's what is measured by ultraviolet visible spectroscopy. X-rays, it's different. Microwaves, we already talked about it. Velocity of light is, you know what? Let me just see if I can use that. Let me see if I can use the pointer. What is the pointer? No, I think I should have done that. oh no, that's only for the PowerPoint. Okay, this is not PowerPoint. Energy of the photon is h nu. Nu is Planck's constant. I mean, h is Planck's constant. Nu is frequency. Frequency is number of waves per second or number of waves per centimeter. Okay, so you can basically substitute for nu here, which is going to be c by lambda. So it can be written as h nu or h c by lambda. So you can see that energy is directly proportional to nu, frequency are inversely proportional to lambda. Okay. We already talked about it, the different rate, the range, radio wave, weakest, microwave, IR, visible, and the red being here, violet being here, ultraviolet, vacuum UV, let's not worry about that, X-ray, and then gamma rays. IR region, we talked about the IR region not in micrometer, but we talked about it in centimeter inverse, the wave number. Wave numbers are proportional to frequency and energy. We already talked about it. You guys need to retain everything that we have discussed. That's important. Covalent bonds vibrate at only certain allowable frequencies, blah, 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 blah. Okay, we talked about, you can read this, but then the numbers that I am concerned about, we already talked about it in the previous class on Thursday. The frequencies, the different bonds that I'm going to be asking you questions from and are relevant, that's something that we have already talked about. We did not talk about this bond, CC bond, and then looking at its number here, nu bar 1200 centimeter inverse. Okay, we didn't talk about it. We did talk about this guy, C triple bond C being at 2200. I gave you a range, 2300 to 2100. So this is something interesting. Like as the heaviness of the atom increases, the frequency decreases. That means it's a weaker spring. Okay, CH, hydrogen is very light. CD, little bit heavier. CC, even heavier. As you can see, the frequency is decreasing. That's pretty cool. I mean, sometimes I forget about that. C single bond C is 1200. I usually don't talk about it. C double bond C is 1660 centimeter inverse. C triple bond C is 2200. The spring is getting harder, tighter, which makes sense. Vibrational modes, both stretching, symmetric, anti-symmetric. This is bend. We talked about different kinds of bends and we had some fun. Fingerprint region. Let's not talk about the fingerprint region. Well, yeah, you can read it when you cannot fall asleep in the night. IR active and inactive. Polar bond is usually IR active. Non-polar bond is in a symmetrical system. Remember that this could show up somewhere in the quiz number 1. Okay. Remember that symmetric molecules are not so good. Okay. Let's skip it. FDIR, skip it. Carbon-carbon bond. Okay. We talked about CC, C triple bond C. Okay, here is an important thing. I want you to report the frequencies of different stretches as a range. I do not want you to say, if I ask you what's the stretching frequency of C triple bond C or C triple bond N, don't say 2200. Write the range that we talked about the last class. Take a note of that if you think you will be forgetting about it. Give me a range, 2200 to 2100. If you accidentally say 2200 instead of 2300 to 2100, if you mess up one number like 2200, very close, I'll still give you full points. But don't say 1600 to 1800 for that answer. That's wrong. Okay, if you're a little close and slightly off, I'll be forgiving in the beginning. C double bond C, there is, I think when we talk about aromatic compounds, then we will talk about it. For the time being, you can forget about these two. Single bond and double bond. Triple bond, you cannot forget. You must remember. Carbon hydrogen, we talked about it. sp3ch below 3000. sp2ch just over 3000. To the left of that line on the spectrum. SPCH around 3300. Okay, this is important. This is an alkane spectrum. The alkane is written here. Normal hexane, CH3, CH2, 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 CH3. All the only bond that it has is carbon hydrogen and carbon carbon. Okay, it's all single bond, so all the carbons are sp3. So sp3ch, see, this is the 3000 mark. You can see my pointer, right? This is the pointer, this is the 3000 mark. See, all the peaks that belong to the CH, like loads and loads of CHs, okay? There are actually 1, 2, 3, 4 kinds, and who knows how many kinds are stuck here. If you look at N-hexane, how many kinds of CHs are there? 1, 2, 3, and 4. So it actually makes sense. There are 4 peaks. The terminal CH3s, that's one kind of CH. The next CH2s, that's another kind of CH. The next inner CH2 is another kind of CH, and the central CH2. So one peak we are missing, but otherwise it kind of makes sense. CH bending. Let's not talk about it. Let's quickly skip to the next slide. I'm just kidding. But yeah, I'm not going to be bothering you about this CH bending. So stretches are all here in this region. Okay, and you can check something important here. 100 to 0. That's transmittance or that's absorbance? Which one? The y-axis. Who can answer?
That's transmittance.
Very good. The down here, that's wave number, centimeter inverse. It says 600 to 4000. Yeah, 400 to 4000 is easier to remember. That's almost there. So if you want to remember it that way, that's fine. Okay, this guy has a double bond. That's a very cool molecule, 1-hexene. There's a double bond. That means this guy is CH2, this sp2, this is sp2. So there are 2 CHs here and 1 CH here. So that's going to show up little over 3000. This little peak, that's the sp2ch. Okay. If you see that, that means you got a double bond. All these guys are from sp3ch, all the rest. This is important actually. The double bond C stretch around 1642 centimeter inverse. That's important. I'm not going to talk about the bend. So for me, for our class, the C double bond C is somewhat interesting and important. This is important and this is important. Okay, it's primarily these two are very important. Let's go look at the other one. Triple bond. Okay, triple bond. This molecule is 1 octane. Whole bunch of carbons, 8 carbons, like octane, like gasoline, but with a triple bond at the end. Because of the triple bond, there is a CH here. That CH shows up here, 3330. So I told you that it's usually around 3300 centimeter inverse. There should be a C triple bond C. That's very important. 2119. You should report, if I ask you that for 1 octane, what kind of stretches will you be expecting? You should say around 3300, less than 3000, and in between 2100 and 2300. That's going to be the C triple bond C. So right below this spectrum, there is an interesting spectrum of another triple bond, but you don't see this peak. And that could be a trick question in the quiz. Why do you not see that? Well, because look at the molecule. It doesn't have a CH. The triple bond is in the middle of the molecule. It's not at the end of the molecule like here. This guy is in the middle, so there is no CH. However, there is a triple bond. So if you don't see that, and if you say, well, I don't have a triple bond, that will be not very wise. All the CH2s are showing up here, but the C triple bond C, which is supposed to show up here, 2100 and 2300, that's not showing up. Why? Anybody has any idea? Why are we having trouble seeing the C triple bond C stretch in this region?
It's symmetrical.
Awesome. Symmetrical. OH and NH stretching, alcohol OH, it broadens because it's hydrogen bonded. Secondary amine, broad with one sharp spike. And primary amine, they show up like two little spikes, but the whole thing is broad. No signal for tertiary amine. This is primary amine, NH2. Secondary amine, NH. And tertiary amine, no hydrogen. Remember that. That's important. Alcohol spectrum. Ooh, look at that beehive. That's OH. What did I say? 3200 to 3600. Yeah, something like that. Or you can, if you say 3100 to 3600, I'm game. No problem. This is butanol, and all the CHs are here, less than 3000. And CO stretch, single bond. I'm so thankful that they have written here unreliable. Yeah, it's who knows what this jungle is, what is going on here. Amine, it's a secondary amine, so it's broad, but it's not like a beehive. It's more like a wasp's nest. Bunch of sp3ch right down here. That could be a bend, I believe, but let's not talk about it. I'm not comfortable. Or it could be an CN bond. Possible. Maybe you can figure it out what this peak is. I think it's a CN stretch. C single bond nitrogen. We didn't talk about it. Carbonyl stretching. Oh, this is going to be lovely. Ketone. What kind of ketone is this? 2-heptanone. CH3, carbonyl, CH2, 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 CH3. So bunch of sp3ch right here. Carbonyl, there is no way you can miss it. Right there. What should you write? If I ask you to write down the important peaks for that, well, you should say 1600 to 1800 centimeter inverse. Don't tell me it's going to be 17, 18. Please don't do that. I want a range. Range it is. Aldehyde spectrum. Yeah, there is something that I always forget. Apparently, the CH stretch, this aldehyde, this guy, aldehyde CH stretch, this is where it shows up like a doublet, two peaks, 2720 and 2820. You know, I'm going to learn it with you guys too, because I always forget about it. Let's learn it and let this be part of our lecture. Aldehyde CH shows up at 2720 and 2820, around that region, where normally alkanes show up. And all the alkane peaks, all the sp3ch peaks are here. Carbonyl is here, this 1720. Ketone was what? 1718. Aldehyde is 1720. Not a whole lot of difference. Carboxylic acid. This is a beehive ever never seen. So you can see that it's almost like bearing the CH stretch. This is where the hydroxide OH peak is here. What's poking out from the cloud? That's not OH. That's actually CH stretch. If the CH was smaller, you wouldn't even see it. There's nothing you can do about it. Okay, and it's highly hydrogen bonded and super broad. This beehive starts at what? 2000, 2100, 2200. You can say like 2200. So for a carboxylic acid, the OH you should report as 2200 to all the way 3600. This range could be the same, 3600, like we usually use for alcohol, but it starts way early, way down here. Carbonyl for this guy is 1711. That guy doesn't broaden. That guy is always sharp. Hexanoic acid. What else is here? This is not a very good resolution. This is an amide spectrum, CONH2. This is interesting. It shows up like two NHs. We can discuss it later on in the course. Why so? Maybe one of you can remind me at the very end of the semester, like, can we talk about the IRs IR spectrum of MI when we talk about MI chemistry. I'm not going to, oh, there you go. CN absorbs around 1200. Where was it in the past? That nitrogen molecule? Where was it? This guy, right? 1400 and 1400, 20, 30, 40, 1460 or so. 20, 40, 60, and 1460. This could be the CN bond. I think that's the CN bond. It's very significant. Okay, let's go back. So C triple bond N, this is beautiful. 2100 within 2300. So that's around 2249. But if I ask you what should be the significant peaks from this IR spectrum of this molecule, you should report two. You should report the sp3ch less than 3000 centimeter inverse and C triple bond N. What should you say? What should be the range of that stretch in the IR? Anybody wants to chime in?
2000 to 2300 centimeters inverse.
Yes, thank you, Carla. 2000 or 2100, if you remember. 2000 is fine for now. Summary, I don't want you to look at that. Okay, this is important. IR cannot determine a structure. That's very true, but at the same time, IR is pretty cool, very important. Some signals can be ambiguous. I hope you have an appreciation for that statement. Functional groups are usually indicated. This is important. If there are 4 answers, okay, what is IR good for? Looking at, I don't know, some ridiculous, I might put some meaningless stuff for question 3 answers. And then 1 answer is you can detect functional groups. That's the right answer. Absence of a signal is a definite proof that functional group is absent. Correspondence with the known samples IR spectrum confirms that the identity of the compound. That's pretty good. Okay. Any questions about IR? Let me stop that for a second. Any questions regarding IR? We do have a quiz on Tuesday, and we have covered IR, so there's going to be a lot of questions from IR. So you already know what we might be asking you for. I'm not going to ask you like something too difficult, but then, whatever we have discussed. If you see some homework problem that talks about something that we haven't discussed, it's not going to be in the quiz. As simple as that. Let me go to the other screen that you guys have. Let me see what you guys have. I'll keep that screen on my middle computer screen. Okay, so let's talk about mass spec. Okay, there are 6 comments on the chat, I think. So okay. Good. You guys are talking about it. Very good. Very good. Okay. Group discussion is good. Okay. So why not we share screen again? I'm sorry, I'm not a big fan of PowerPoint. It's not even PowerPoint. Okay. Let's move to the next slide. Mass spectroscopy. Okay, mass spectroscopy. I'm going to switch to the screen today if possible. Or we might just go through this presentation and see how far we can go with the mass spec. We may not need to go to the board because I really want to, unlike in the past, I don't want to spend way too much time on this. Mass spectroscopy is a way you can figure out the mass of a molecule. It's very useful. Okay. So what does mass spectroscopy do? Are we using any electromagnetic radiation? That's not the case. Remember that there could be a question like, we use electromagnetic radiation for, you're supposed to pick the wrong line. Like, which of the following techniques does not use electromagnetic radiation? Then I have for A, IR, for B, NMR, for C, mass spec, and for D, UV visible. Okay, the only technique that's called spectroscopy or spectrometry, but we don't use the electromagnetic radiation is mass spec. Okay, so that could be a question like that. I'm just dropping some hints. Molecular weight can be determined from a very, very small sample, like microgram. Unbelievable, right? 1,000th of a gram of a compound can be used, 1,000th of a milligram can be used to determine your mass spec, which is awesome. You lose nothing. It does not involve the absorption or emission of light. This is very important. This second line, you need to really get it in your system. Otherwise, you might lose 3 points in the future. This is very important. No electromagnetic radiation business is going on here. Different from IR, different from NMR, different from UV visible spectroscopy. A beam of high energy electrons breaks the molecule apart. It sounds like a very torturous, it sounds like some kind of violent procedure. It's true. You use a very strong, high-powered electron beam to basically knock off an electron from the molecule. You might be asking me, like, where does that molecule, that electron come from? It doesn't matter. It could be breaking a bond. It could be knocking off an electron from a lone pair. Who knows where? It just, one electron is knocked off. When a molecule loses an electron, what happens to it? It becomes positively charged. That's the whole idea. You forcefully make an ion out of the molecule. Okay, and then what happens is sometimes the molecule breaks down into multiple pieces. If I lose, I'm just going to switch to the screen. Okay, so let me go back to the board. I'll show you a few things so that you can understand. Okay. So let me erase this, what we have on the board. Okay, so 128B, and today is February 9. Okay, we are talking about, let me use the purple color, mass spectroscopy. What this does, I don't like that line, sorry. Okay. Mass spectroscopy figures out the mass of the molecule. Okay. If you have a molecule like this, what's the mass of it? How do you figure it out? 12 times 6. 6 carbons, right? Times 6. 17 AMU. And how many hydrogens in cyclohexane? How many hydrogens? You shouldn't be thinking too much.
12.
So the total mass is approximately, it's not correct because you have to take care of the isotopes and their relative abundance and this is a very crude approximation. 84, okay? 84 units, atomic mass unit, right? So mass spectroscopy, when you see a mass spectrum, I'll just give you the final deal first, okay? Instead of building up the story. If this is a mass spectrum, the x-axis is nothing but mass. So it starts from, I don't know, maybe mass 50 to, it could be 500, okay? These are the masses. So this is 100, 200, 300, 400, 500. This is 100, 200, 300, 400, and 500 atomic mass unit. This is the y-axis. We'll talk about the y-axis in a second. Okay. So if we do a mass spec of, what's this molecule called? I'm just checking on your 128A situation. Who remembers from your past life in 128A? What is this? What is this molecule called?
Isn't it just a cyclohexane?
Cycloalkane.
Cycloalkane is the family. This dude is called what? You cannot ask. You answered the right answer. Carla?
Cyclohexane?
Cyclohexane. Be confident. Cyclohexane. Since we are talking about cyclohexane, and cyclohexane happens to be one of my favorite molecules. Is it flat, planar molecule? Is that the right representation of its three-dimensional shape? What does it look like? You hear what's moving? This is where I sit in my office. What is the shape of cyclohexane in 3D? Who remembers? All gone? Come on, guys, you're scaring me.
The chair?
The chair. Yes, the chair. And it looks like this. Chair has two kinds of hydrogens. What are the two kinds? Trust me, I'm not going to waste like 15 minutes on it, but just asking you some questions.
Axial.
Equatorial.
Axial and equatorial, very good. Axials are pointing up, equatorials are like down and up, down, up, down, up. Like it's like if I'm wearing like a crown, then the three axials are pointing up, so receiving signals from my planet and from my spaceship that my family has riding, they're trying to come and get me, and three pointing down like the three landing gear, and the one equatorial is up, the next equatorial is down, up, down, six of them, six slightly up, six slightly down, and it's called equatorial because it's in the middle of the molecule. Okay, just checking. Okay, if we do a mass spec of this, if this is 84, if this, I don't know, this is 50, let's call it 0. If this is, sorry, I'm not trying to send any signal with the color coding. And this is 50, this is, I don't know, 75. Let's say this is 84. So you get a peak at 84. Okay, so if you see a peak at 84, then you know that's my cyclohexane. Okay, so I'll just make it color. Okay, that's at 84. So when you look at that, you know that I have a compound that's mass is 84. Sometimes because the molecule falls apart and breaks down into fragments, sometimes you can miss the mass of the compound, but let's not talk about it until we get there. So this is just a very crude representation of what a mass spectrum look like. Mass spectrum is not like infrared spectrum where things hang from the top like a little icicle. It's not upside down. Infrared spectrum is not this way. It's upside down, right? The peaks are going from roof down, and this is going from floor up, right? So these are the peaks. Okay. So this is an extremely crude representation of a mass spectrum. Okay. We will talk about it soon. The y-axis. Let's not talk about it until we talk about how it happens. So what happens is, let's say if this is the mass spectrum, mass spectrometer. Let's say this is the mass spectrometer, and my drawing will be super crude. Okay, and let's say the mass spectrometer, this is where you inject your sample, or this is where the sample goes in. Okay, so there is a little port, and you use actually a syringe. Okay, you use a syringe with a very sharp needle in the front, and it's actually not sharp, it's a flat head. Okay, you put your sample inside, whatever the sample is. Let's say we have a compound. You put that compound in here, okay, a dilute sample solution, and you inject it into here. The sample is injected through the injection port, or whatever the sample loading zone is called. Okay, can somebody name that molecule? 1, 2, 3, 4, 5, 6, 7 carbons with a branch. Who remembers how to name branched alkanes?
2-methylhexane.
Can you say that one more time, a little more loudly?
2-methylhexane. Okay,
just checking, make sure that everybody else knows. It might haunt you like a bad dream from the past. Okay. 2-methylhexane is dissolved. It doesn't matter whether, this is cool. It doesn't matter whether it's liquid or solid. You dissolve it in something. You dissolve it in methanol. Usually you dissolve in a solvent. Let's say methanol. Okay, because methanol doesn't screw up anything inside the mass spectrometer. Okay, it's inserted here, and this part is heated. Okay, it gets into the gaseous phase. It gets into the gaseous phase. Okay, and then it enters into a chamber, and there is a carrier gas. So there is a carrier gas that's flowing through it. That could be something like an inert gas such as helium. Helium doesn't bother anything, doesn't react with your compound because helium is inert. That's what I'm teaching Chem 8 and Chem 128A students at this point. Like I taught them all that stuff right now. Helium, neon, argon, krypton, xenon, they're inert because their shells cannot take any more electrons. So they have zero motivation to make bonds with anybody else. They don't care. They're the celebrities, right? So helium gas carries your sample, whatever went in here, is 2-methylhexane dissolved in methanol, it goes in there. Helium is taking it there, and it's heated up. So the liquid becomes a vapor. It's vaporized. The vaporized stuff is now entering at some point a chamber. It's passing through that in this direction. Okay. In this at some point, this is a very crude demonstration. You as your compound in vapor phase is traveling this direction, left to right. Okay, you hit it with an electron beam, what we were just studying on the PDF, on the PowerPoint presentation. There's a cross street. Imagine just you're driving through a cross street, and there is something going on across that path, some kind of movement, and you are hit by that wind. Okay, so over here, I'm just going to say helium. This is helium. So helium is basically carrying everything this direction. And over here, everything was liquid. And once it enters through that hot, like whatever that heating coil is, it goes to the gaseous phase. Okay. Down here, it's gas or vapor. Okay. The vapor is passing through this area. And in this green region, high powered electrons are flowing. There is a beam of electron. Okay, so imagine the molecule is flowing and you're hitting it by a very, very strong current of electrons. They're passing from one to the other direction. And as that hits the molecule loses an electron. This is where it took me a long time to figure that out. Okay, as your molecule, goes in methanol, okay, first liquid, then heat, then gas, then it's attacked by electrons. Electrons or electron beam. Okay. At this point, as the electrons are hitting it, it loses electron. That's the key. Once I lose an electron from some part of my body, what happens to me? I haven't lost any proton. Let's say I have a CH3 here, I have a CH2 here, I have a CH here, here is an OH, and I don't know, my entire body is made out of carbon, hydrogen, oxygen, nitrogen. There are lone pairs, double bond, single bond, blah, 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 blah. And I'm hit by electron beam and I lose an electron. The moment I lose an electron, none of my protons has been messed with. I still have the same number of protons. So what happens? I become positively charged. So at this point, well, this was bad planning. Let me just redraw it. This is what happens when you're not planning very well. I'm just going to make things smaller, okay? So just bear with me. Never mind. So this molecule, liquid in methanol, that's a solvent. It's also liquid. Injected. Heat. You know what? Let me use color. So this chamber is heated. It's passing through it. Came out as a gas. Then it's still flowing with the help of helium. Helium is the carrier gas. It's taking it in this direction. And now it's hit by electron beam this direction. So as these vaporized molecules are passing through, this is when it loses electron. And the molecule, whatever the molecule is, I'm just going to call it M. This is the mass of the molecule. The molecule loses an electron, so it becomes a charged species, or a dot. One dot is gone. It has only lost one electron. It's called a radical cation sometimes. Okay, we will go back to the PowerPoint and follow up with what we are discussing right now. And then So the bottom line is this. I have a methyl group here, a methyl group here. I have a CH2 here, CH2 here. I have an OH here. My tummy may have an amine, and my legs are made out of, I don't know, a CH2, 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 something with a sulfur at the end, okay, my feet, okay? So I might be made out of different body parts, different functional groups. The moment I am stable when I'm a wholly neutral compound, when I lose an electron, I start undergoing an instability phase. My whole body after losing an electron becomes extremely unstable and things start to fall off. OH can fall off, a CH3 can fall off as a methyl group, or CH3 plus or something like that. We will show you that. I don't want to talk about everything because I think the PowerPoint is pretty useful here, okay? So I start falling off as fragments, okay? The fragments that are charged, when you have this radical cation, when it breaks down, this is what happens now. It starts to break down. Breaks down into fragments. Not in all mass spectroscopy, okay? Somebody, if you're talking to some uncle or someone and who is working for an ag company or an analytical company, he or she might say, that's not true. We do LCMS and ESI, electrospray mass spectroscopy, molecule doesn't fall off. So if that person says that to you, don't argue, it is true. What he or she is saying is true. Some mass spectroscopies use very soft ionization. When you do a soft ionization, very delicate molecule, you don't want the molecule to fall apart into 1,000 pieces, then you use soft ionization. You just make little charge and the whole darn molecule flies, okay? So once you make that charged species and it breaks down into pieces, then you create a potential, okay? This guy enters into a tunnel. These radical ions and all the breakdown into fragments, some of the fragments are charged like a cation. Some of the fragments are radical ions, okay? And all of them start flying through a tunnel, which has positive charge here and a negative charge here. So these guys, all these guys start flowing through a tunnel. This is like a tunnel. They all enter here, which is a potential. Imagine that this end is positive and this end is negative. So the negative is pulling all the cations. So they start flying through it, super fast speed, okay? And what happens is all the different fragments are flying through them, and then there is a turn. In the turn, what happens to a truck, 18-wheeler versus an SUV versus a four-door sedan versus a two-door sedan versus a sports car versus a motorcycle? Okay, the ones that are heavy and bulky and bigger mass, do you think they can take the turn sharply? Or they can, so some of these dudes, some of these guys will be going here, okay? Some of these guys will be going here because they can, the ones that cannot take the turn very sharp. The ones that can take the turn sharp, they will probably go here, okay? Because they're being pulled. The heavier ions will be over there, okay? And then down here, you have a detector. This is a detector. Okay, I forget that that's my line. This is a detector. And the detector has already been calibrated with some known compounds with known mass. And it knows that this is mass, big mass. This is like 1,000 AMU. In the middle, it's 350 AMU. Down here is 50 AMU. Okay, the scale has been kind of figured out. So as this whole drama happens, entering into the injector as a liquid, dissolving in a liquid, and as I said, this is like it uses micrograms. Microgram is 1/10⁶ gram. So basically, what is it? 1 million? 6 zeros is what? 10 million, 1 million, something like that. 1,000 of 1,000 of a gram. Okay, 1,000 of a gram is milligram. 1,000 of a milligram is a microgram. Tiny, 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 tiny little amount. You lose nothing. Okay, where are we with time? Okay, we are good. That enters, it gets heated up, goes to the gaseous phase. Eventually, it's hit by an electron beam. It's being carried with helium. It's flowing in that direction. Electron beam hits it, knocks off an electron. Then it becomes a radical cation. Then it starts breaking up into smaller fragments. Some of them are positive, some of them are radical ions, and they start flowing through them. And the cations are being detected at the end with a detector which has been pre-calibrated. And then eventually the data is processed and you see a nice spectrum. Okay. Let's stare at the board maybe for a second, and let's go back to that presentation. I'm going to sit down. I talk too much. I need a break. That's my lifelong concern. Okay. I'm going to go back to the front camera, and I'm going to again share the screen. I think it'll probably make more sense. Okay. Mass spectroscopy, molecular weight can be obtained from a very small sample. Doesn't involve the absorption or emission of light. Remember that, that's important. A beam of high energy electrons breaks the molecule apart. Masses of the fragments and their relative abundance reveal information about the structure of the molecule. What kind of body parts you collect? This is like a crime scene. Sorry, I'm making it more morbid and disgusting probably than what it has to be. Yeah, so it's kind of like a crime scene. Like, oh, we see a hand. That means it was born with a hand. We see like something that could have been a head. It's basically that. Okay. Electron impact ionization, high energy. Yeah, this is really cool. Electron impact ionization. High energy electron can dislodge an electron from a bond, creating a radical cation. Positive ion with an unpaired electron. So don't get confused looking at this particular slide. Electron hits an ethane molecule, CH3CH3 or C2H6. This picture or something like this picture used to confuse the hell out of me. Like, what does it mean? It means nothing. This powerful electron, the electron beam, has knocked off an electron from this particular bond. Imagine that this CH bond is made out of two shared electrons. One electron has gone bye-bye. Okay? So this guy is left with some weird situation. A carbon with an electron, hydrogen with an electron. The bond should have been 2 electrons, but it is essentially torturing a molecule. It lost that, and once you lose an electron, you are bound to become positive. You become positive, right? Then so that could have also led to a different scenario. It could have led to a cation, complete cation, if the leftover bond electron stays to the side of the hydrogen. If the hydrogen got hold of that electron, then you would create a radical hydrogen, right, on the right side, and a nice ethyl cation. Make sense? Let's pause for 10 seconds. So this is one path. If this bond was affected, see my cursor here? If this bond was hit, you don't know which bond is going to be hit. There is no such rule. If this bond was hit, then this part of this bond gets completely ruined. You lose an electron, and that electron could stay on this side or this side. You could have produced a proton and a radical here. Okay, they just showed this scenario. You produced ethyl cation and a hydrogen radical. The hydrogen radical does not fly through the tunnel with the charge. Only this guy flies. Okay. Another scenario is looking at the situation down here.
I just needed to put in there. I was waiting for the tortillas.
In order to have this scenario happen, you need to have the middle bond hit by the electron beam. If the middle bond is hit by the electron beam, same horrible thing happens to that bond. Lose an electron, you make an electron, you have one electron left. That single electron stays on one side, and the other guy gets the short end of the stick, becoming a positively charged cation. Cation flies. Okay. So this is how the fragmentation happens. Once the electron hits the molecule, then all hell breaks loose and mudslide starts. Okay, the window falls off, the door falls off, things of that horrible nature start to happen. Separation of the ions. See, this is the path. This is like the magnetic field. There is like a little potential. I didn't say it correctly. So if I misspoke, just correct me. There's a magnetic field, there's an electrical field because of the magnetic field, and the heavier atoms go along the periphery, smaller atoms take the sharper side. Have you guys, if you guys are mechanically inclined, you may have heard about differential gear. Do you know what differential gear is? You have no idea. Shame on you. Differential gear is like in the older days when you had rear wheel drive. Most cars used to be rear wheel drive. Still, that some sports cars are rear wheel drive. Okay, so when you are taking a turn, let me just quickly. I'm going to torture you to the end. Okay, so if this is the car, my palms are like the front wheels, and my elbows are the rear wheels. If I enter a turn, right? If I enter a turn, my left side of the vehicle is going through a smaller circle, and the right side of my vehicle is going through a bigger circle, right? So this is the smaller radius and this is the bigger radius. So actually to get to that same point, the outer wheels have to go at a faster speed, right? The inner wheels, if I'm taking a turn this way, these two wheels must be spinning slower than the outer wheels. So the drive shaft, in the older days, the rear drive shaft used to have a differential gearbox in the middle of the axle, which has a fantastic mechanism. Which whoever invented differential gear, he's a genius. He's incredibly genius. It's like a little two gears facing each other. Then you have a little thing in the middle. As the wheels turn, one guy slows down and the other guy speeds up. And the main axle that's powering the rear wheel doesn't have to flip out or freak out at all. It just does its job, and the wheels change their speed as it's taking a turn. One wheel turns faster than the other, whatever the difference is. And it's one of the most ingenious and brilliant inventions of mechanical engineering. That's why I have so much respect for mechanical engineers. So it's kind of like the same. The guys who are going to the outer surface, they're going at a slower speed. It doesn't matter. They don't have to keep up with everybody else. They can land a little bit later. Okay. But by seeing the deflection down here, by seeing like which ion has been caught where on that scale, it can basically, I'm going to share screen again. Okay, depending upon where the ions land up, where is my pointer? Okay, right here. Depending upon where exactly the ion lands up, and from the pre-calibration with known ions, known mass of ions, the detector can figure out this is 84, this is 96, this is 92, this is 150, something like that. separation of ions. Only the cations are deflected by the magnetic field. Amount of deflection depends on mass divided by charge. Since only one charge is generated, since one electron usually gets knocked off, it's usually the same number as its mass. If my mass is 84, my m by z will be 84 divided by +1, 84. Make sense? So m by z is what is measured or looked at. Detector signal is proportional to the number of ions hitting it, okay? Because more ions means bigger signal. Less ions means smaller signal, okay? That's very critical. Try to remember that. By varying the magnetic field, ions of all masses are collected and counted. I don't know exactly how it's done. So this is how it is. Okay. Probe goes in there, ion source, blah, 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 then electron beam, then it goes in there, all the little things, they go in, all the ions, ion beam, insulator, I don't know what that means, accelerator plate, it speeds up, the sample goes in from here, enters into that varied electric potential or magnetic thing, and there's a reason for it to be angled, and this is where this during this turn things are actually separated. So it's kind of like, you know, like usually the car or motorcycle races, they involve a lot of turns, like which rider can take the turn more amicably or more effectively. So it's like that's how it happens. Ions that are too light to bend too much, ions that are too heavy that bend too little, flight tube, detector slates, detector, blah, 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 and then all the electronics happen here, and this is the recorder. This is how the mass spectrum, this is how the mass spectrum look like. Okay, I don't think I'm going to go back to the board again. Masses are graphed or tabulated according to their relative abundance. That means, okay, what molecule is this? This is 2,4-dimethylpentane. 1 dimethylpentane, 5 plus 7. 84 plus how many hydrogens does dimethylpentane have? 14, 16. Yeah. So 7 carbons, 84 plus 16, 100. So its mass is approximately 100. So important for the quiz. The biggest mass that corresponds to the whole molecule, not the fragments, that's called the parent ion. Parent ion is this guy, 100. Make sense? I'm going to pause. I'm learning how to pause. Even our son mocks me. Like, you don't pause, Baba. I'm like, okay, I'll try to pause. I'm pausing. I paused. That's that. Okay. Now, you see, like one particular peak is hitting the roof. Okay, that particular peak. That peak happens to be the fragment that, how do I say, there was maximum number of that ion, whatever this peak is, 41. That 41 mass fragment was produced in largest quantity, and it hit the detector like a storm of mosquitoes. That should make Michael happy. There's a special reason for him to be happy about mosquito and off and beat and things of that sort. Okay, so this was the largest flock of mosquitoes. I don't know if you describe bunch of mosquitoes as a flock. Anybody knows if I'm right or wrong? How do you call like a group of mosquitoes?
Probably a swarm.
Swarm of mosquitoes. Okay, flock of birds. Okay. This fragment is little less. It's still pretty good. So the guy, the particular fragment that's the biggest, the tallest, mass spectrum, the software makes that the tallest peak. You heard me, right? The most abundant fragment, ion fragment, shows up as the tallest peak and that's made the tallest peak. That's 100% abundance. Got it? So the y-axis is percentage abundance with respect to the most abundant ion. Does it make sense? So 41 was the most abundant ion. That became 100%. Let's say there were 1 million ions of 41. And then there was 950 million, then 990,000 43. So this is whatever, 9.9% of that. Then this one was, let's say, 500,000 ions of 57. So that became half the height. And this guy was 100,000 ions of the parent ion. So that became 10%. I'm just throwing some arbitrary numbers. Does it make sense? Though, so the tallest peak is also called, very important, base peak. This is very important. You need to memorize it. The tallest peak is base peak. The biggest peak, the mass that shows the mass of the compound, that's called the parent ion or molecular ion. Remember the word parent. Okay, and these are different fragments. 100 minus something is 85. Who can tell which body part this is? What happened to this fragment? What did it lose? Who can figure it out? Something got lost from 2,4-dimethyl and it produced a fragment that weighs 15. The 15 went off and it was left.
Probably a CH3.
Who says that? Cameron?
A CH3? Yeah.
It lost a CH3, so this is 2,4-dimethylpentane minus CH3. You guys can actually start playing with it, like what is 57? So 100 minus 57 is 43. You also see 43. You also see 41. You need to start putting into account that hydrogen's abundance, and its isotopes abundance is not that important. Hydrogen is the most abundant isotope between hydrogen, deuterium, and tritium or tritium. I forgot what the American translation is. We was born in India, then came here, then went back, then came back here. I'm all mixed up right now. Okay, so you can figure it out. So all these tiny little things, they are probably contributions from isotope situation. And sometimes when you have certain isotopes like carbon, it's mostly 12. 12 is 1.1%. 90. What's the percentage? Michael, C13 is 98.9. No, what's the number? Carbon, it should be down there. Carbon is 12. Carbon 12 is 1.11% abundant, and carbon 13 is.
Yeah, you've got it backwards.
Yeah, carbon 12 is 98.9% abundant. Carbon 13 is 1.11% abundant. So there is 1.11% carbon 13 where the mass will be 1 unit more. So I don't want to overwhelm you. Just let's learn the basics right now. Okay. Parent time, x-axis is m by z. Z is usually 1 because you only lose you only develop 1 plus charge. So the value of the z, this is mass m and z is charge plus 1 usually. So m by z is usually m. Okay, you don't have to factor in anything. So this is what is being measured by the detector. Y-axis is abundance with respect to the tallest or the most abundant peak. Most abundant peak becomes the tallest peak, and that's called the base peak. So important, base peak, parent time, x-axis, y-axis. Got it, everybody? I'll pause for 10 seconds. This is very important. This is very, very, very important. Okay, that's the mass of this guy. So 57 happened when something like 43 fell off. You guys can figure out what 43 is. How many carbons and how many hydrogens? 2 carbons is 12 times 2, 24. It might have had 3 carbons. 3 carbons means 12 times 3, 36. 36 and 11 hydrogens. C3H11. That could be a fragment. That's a propyl group. No. C3 and 11 hydrogens is not possible. That's impossible. What am I talking about? 4 carbons. 48. C4. 48. 57 minus 48 is what? 9. C4H9. It's a butyl group. This is a butyl group. That means out of the pentane, how many carbons are here? 1, 2, 3, 4, 5, 6, 7. So this guy has 4 carbons. So 7 minus 4 is 3. So a C3 fragment has fallen off and created this fragment. So a propyl fell off, leaving the butyl ion, which got detected here. So fragments tell you some stories. Cyclohexane will probably not disintegrate like this, in a different way. Okay, so this is how the mass spec kind of works. Okay, 444. GCMS, we will talk about it on Thursday. We're going to talk about some, this is very important, you guys can actually look at it. The isotopes of bromine and isotopes of chlorine, and not so much about hydrocarbons. This is where I mixed up. Carbon 13 is 1.11%. Okay, we're going to discuss it on Thursday. We're going to start talking about, I'm thinking about taking a break from spectroscopy, a little break. Let's finish. Okay, let me stop sharing. Let's finish talking about mass spec on Thursday. Let's take a little break and we'll discuss alcohols because I'm thirsty. Okay, we'll discuss alcohols and then we'll go back to NMR. How about that? This will be a break from spectroscopy. I think we can all appreciate a little break from spectroscopy. So we'll discuss mass spec a little bit longer on Thursday afternoon, and then we'll quickly switch gear to alcohol. Alcohol, you will see a lot of familiar chemistry from the past. Very similar to substitution and elimination. You just have to kind of mess with the alcohol a little bit. You have to kind of tame the alcohol in a certain way. We're going to discuss the group. We're going to discuss its hydrogen bonding, then we'll go from there. We will discuss some IR. We might talk about a little bit of mass spec, just a little bit, and then talk about how to make an alcohol, how to react an alcohol, and what are the reactions of alcohol, usually fatigue and unexplained happiness in the next morning, and hangover from some alcohol. Okay, I don't think you need me anymore. You can lose me and have a wonderful evening. I'll post the pictures of the recording. I'll see you guys in 2 days, less than 2 days. Take care.